Hello, I'm Sato from RIKEN Center for the Computational Science. Today's I'm going to talk about in a quantum high-performance computing hybrid platform. As a case study, I'd like to present our project, JHPC Quantum Project, towards the utility scale, Quantum-HPC Hybrid Computing. So let me start with the introduction of our center, RIKEN Center for the Computational Science. One of the missions of the R-CCS is to develop and running the Japanese flagship supercomputer. Current flagship supercomputer is Fugaku supercomputer. This is the picture of the Fugaku, and the public service of the Fugaku has started from March 2021. This system is almost 4 years old. This system is the huge scale, many core based parallel system with the more than 150,000 nodes. And the number of core is almost 7 million cores. Peak speed is that almost half exaflops in a double precision and 1 exaflops in a single precision. Why quantum and HPC hybrid computing? So we are aiming to quantum-centric supercomputing. So my background is the computational science, computer science, and a supercomputer. Many problems can be solved using a supercomputer, but problem require exponential execution time cannot be solved even using the supercomputer. So these problem is including quantum simulation and a full optimization problem, and a graph problem, cyclic analysis, and factorization. So when solving the large and realistic scientific problem using the quantum computer, combining with the HPC is required for the many kind of the computation, including pre-processing and post-processing. So in many quantum many-body problem, the computation which generates a model is well suited to the supercomputer and sufficiently fast. If you consider the realistic the application and the speed up and the scalabilities, replacing everything with a quantum computer is not practical. And in the future, the number of qubits getting large. In that case, HPC will be necessary to prepare the state of the quantum. And particularly in quantum chemistry and material science, combining quantum computer with the existing the quantum chemistry application on the HPC, which compute an approximate solution, is essential. So effective use of the quantum computer is including the first obtaining in a variational state approximate close to the in a ground state, true ground state, using the HPC. So and then make use of the quantum computer. And similarly, for energy calculation on a large molecule, it is necessary to identify the portion truly required the quantum computer. Our project is JHPC Quantum Project is started from 2 years ago. This is the 5 years project, and the project is funded by the NEDO. It's the funding agency managed by the Minister of Industry and Trade in Japan. The member of our project is RIKEN, ours, and SoftBank. This is a telecom company, and the University of Tokyo and the Osaka universities. And the mission, first, the development and the research on a system softwares to connect and integrate quantum computer and supercomputer. Not just the development of the system software. Using this system software we develop, that we are building actual quantum supercomputer hybrid platform with the two types of the quantum computer. One is IBM, and another is the Quantum. And this supercomputer was already installed in on-premise in Japan. And we are going to connect several supercomputers, including the Fugaku and the University of Tokyo supercomputer, Osaka universities, and SoftBank to these quantum computer. And as a scientific goal is to demonstrate quantum advantage. And quantum advantage of Quantum-HPC hybrid application against the existing application which is running only a supercomputer. And we are also interested in the concept of the quantum utilities. It means that how useful current the quantum computer by combining supercomputer. And also the outcome expected at the end of the project is that to commercialize our system to provide a service of the next generation of the internet. This figure shows our platform. The quantum IBM machine is installed inside of R-CCS, and this is connected to the Fugaku, and also we're in a middle scale of the GPU system. And the ion trap quantum machine is installed in a different campus called the Wako campus. This campus is 500 kilometers away from RCCS. So this machine is connected through the internet. And using the internet, we are connecting it to the supercomputer of University of Tokyo and Osaka University and SoftBank. This is the picture of IBM machine that we installed in RCCS. So QPU is installed in the system 2 rack, and the QPU is the Heron Revision 2, the QPU, with the 156 qubit. This system is installed in the June in this year. And this picture shows the quantum ion trap quantum computer. This picture is the clean room which installed in a ion trap quantum machine. The name of this machine is RAME, and this is a chip, and the chip is installed in a vacuum chambers like this. Okay, next is how to program the combining quantum computer and supercomputer. It means the programming model for HPC and a quantum hybrid application. The many current quantum computer users using the quantum computers through the cloud. So the users and the programmers is logging into the cloud and running, for example, Qiskit, the application on a single node. And the Qiskit program is connected to the quantum computer like this. And the users using the quantum computer. If you think about how to combine with the supercomputer, we propose two programming models. One is the loosely coupled model, which consists of independent program of the quantum computer and HPC in a form of the workflow. So this figure shows the workflow of the independent program. The program can be the large-scale MPI program running on HPC, and it can be the quantum computer program. It can be very simple, the single node program. But anyway, these independent program is controlled by the workflow to execute the HPC quantum hybrid program. And next, another the model is the tightly coupled the quantum and HPC in one HPC program. So request from the supercomputer is connected by a remote procedure call form, and for the offloading the quantum computation to the quantum computer like this. So these two programs is running simultaneously and coupled the tightly, and it's provide a more efficient and a well controlled the execution of quantum and HPC. This figure shows our software stack. There is two ways to access the quantum computer. The one is our SQC APIs. SQC API is using the remote procedure call, and RPC uses the direct access API provided by the QPU vendors, IBM and Quantum. And another way to access the quantum computer is just a REST API, which is usually used in the cloud. We are supporting the three kinds of the workflow tools. One is the TEACRISE by the Quantum and the prefect general purpose the workflow tools, and the scribe is the Japanese-made workflow tools. And we also provide the quantum computer software libraries, and also we are supporting the error mitigation and suppression, which is provided by the Q-Control and KEDMA. This figure shows the overview of our JHPC quantum system. The heart of our system is the QC request schedulers right here. At this schedulers, that we support in two kinds of function. One is the authentication of the users by using the JWT token, and also the priority management for the request coming from the HPC in a single node. So if request coming from the supercomputer HPC, this request is the executed high priorities to avoid idling time. And another request coming from the single node, paired chip node, is executed in a low priority as a background. And this priority scheduling is required to support an efficient execution of the tightly coupled programming model, as explained in the previous slide. And we are also supporting to the multiple supercomputer. So for example, the one supercomputer University of Tokyo, Miyabi, and another is the Fugaku. So we implement the coordinated schedulers to coordinate in the request from the multiple supercomputer here. And if Fugaku and University Tokyo supercomputer Miyabi, the request schedulers, these scheduling is coordinated by this global schedulers. Okay, next, let me talk about quantum and HPC hybrid application and our experience. As you know, current the quantum computer is a NISQ machine. It has a limitation on algorithms. And we are focusing on two kind of the application area. One is the quantum chemistry, another is the machine learning. For the utility scale, the Quantum-HPC hybrid computing, let me talk about the more detail on a quantum chemistry application. So one is the ground state calculation of the cluster of the ferrite and the sulfur by the sample-based quantum dynamization algorithms. This is the effort of quantum centric supercomputing with IBM and RIKEN. And this is the very good demonstration of a tightly coupled programming model, how to use the large number of nodes of the inner HPC. And next example is biomolecule chemical reaction analysis by using the Quantum-HPC hybrid computing workflow. This is the effort by the Quantum and RIKEN, and this is the good demonstration for the loosely coupled model, the quantum by Quantum Tercrise workflow tools. This experiment is using the sample-based the quantum diagonalization, the algorithms. This algorithm executing the many sampling on a quantum computer, and the sampling is sent it to the supercomputer to calculate the ground state by large-scale diagonalization. We already demonstrated to incorporate an quantum computation of the chemistry in a quantum-centric supercomputing architectures using up to 66,000 and 4,000 nodes of the supercomputer to assist the Heron, the superconductive, the quantum QP, the processor. This study is calculation is performed on a supercomputer using the quantum computer result in separately. But in this summer, we execute the more large-scale computation, and execution is done on the large-scale HPC. And also, we did the iterative calculation with the tightly integrated by exchanging data at runtime. This slide shows some highlights of the SQD demonstration for evaluating the energy of cluster in ferrite and sulfur with a new diagonalization in a quantum subspace using large devices and increasing the complexity of the workflow. Here, we implement the new diagonalization program by MPI while using the large number of nodes of the Fugaku. And we have the 10 to the 9 dimension the diagonalization. And also we did the overlapping between the CPU and the QPU computation by tightly coupled the model using almost the 160 the nodes of the Fugaku, the integration with the Fugaku and the Heron. And this slide shows the overview of biomolecular chemical reaction analysis using the NTChem HPC application of the Fugaku and the the quantum computer. To analyze the large molecule, we are using HPC, the protein backbone. And then the reaction center is computed by the reaction center is identified. Then this part is computed by the quantum computers more precisely. And this program is programmed by the workflow using the quantum telecrisis workflow tools like this. And now 2 years passed. Then we are now in the middle of our project, and the installation of the quantum hardware is already done in the second quarter of this year. And currently, we are deployed our system softwares to make the Quantum-HPC Hybrid Computing Platform. In the next year, we are moving to the full-scale operation. And our system is almost available. And we started the test users program to invite the external users who are interested in a Quantum-HPC hybrid computing. International collaboration is welcome. And this is the conclusion remarks. Again, when solving the large and realistic scientific program using a quantum computer, the combining with the HPC is essential, and particularly in quantum chemistry and material science application. Combining the quantum computer with the existing quantum chemistry application on HPC is very, very important and essential. To execute this kind of the problem, we proposed in the programming model. One is the loosely coupled one, and another is the tightly coupled one. And these models are already supported in our platform. And in this presentation, we present 2 case studies. One is the ground state calculation of a cluster of the flight in sulfur by new algorithm sample-based quantum dimerization by tightly coupled programming model, and also biomolecular chemical reaction analysis by Quantum-HPC hybrid computing workflow. Thank you for attention.